All right. So we're looking at the limit as x approaches 0 of 3x over the cube root of x plus 8 minus 2. So what's the first thing you should do with this limit? What's the first thing you should do?
Plug in 0.
Lots of people saying different things. I heard the right thing, which was plug in 0. First thing we should always do is plug in the number. So what do we get if we plug in 0? We get 0 over 0. So we now know that it's indeterminate, which means we need to do something else. And then I heard somebody else say multiplying the top and bottom by the conjugate of the bottom, which is definitely one of the techniques that we normally use. But unfortunately, multiplying by the conjugate only works when you have square roots. Well, not only square roots, but it doesn't work with cube roots. So if I multiply by cube root of x plus 8 plus 2, I'm still going to end up with a term that's like x plus 8 to the 2/3 power. And it's just going to be an even bigger mess than it was when we first started. So we got to find a different way other than using a conjugate there. Any ideas?
As the power to 1/3.
Say that again.
Isn't like root 3 like to the power of 1/3? Could you take that out?
Okay, so since it's not around the entire thing, since we're only raising the x plus 8 to the 1/3 power, not the 3x or the minus 2, we can't pull it outside of the whole limit, unfortunately. But that's a good thought. What we are going to do is we're going to make a substitution. We're going to get rid of some chunks of this. In fact, we're going to get rid of anything that's an x and turn it into a different variable. So we're going to let u equal something and do a substitution. Remember we did the u substitution before with the trig limit to begin with? We're going to do a similar process here, except we got to figure out the right thing to substitute out. So what part of this is the biggest pain, do you think?
X plus denominator.
Yeah, the denominator, and particularly which part of the denominator?
The cube root.
Yeah, this cube root of x plus 8. So how about we just get rid of that? Anybody got a problem with me just getting rid of that? We're going to say a limit is something, something. We're going to have something in the numerator, u minus 2. U minus 2 is a lot better than cube root of x plus 8 minus 2, isn't it? Yeah. Do you guys agree with that?
Yes.
Yeah, I think so. So then the question is, what is u approaching? So as x approaches 0, what is u approaching?
Two.
Should be approaching 2, right? All we got to do is plug it in here. If x is 0, then this is 0 plus 8, which is 8, and you cube root it to give yourself 2. So this is now a limit. The limit is u approaches 2 of 3x over u minus 2. Now, 3x is a little bit of an issue, right? Because my limit is u approaching 2. So can I get rid of the x somehow?
Can you solve the u equals root 3 of x plus 8 for x?
We can. So what we'll have to do, we'll have to cube both sides of it, right? So that'll give us u cubed on the left, and it'll give me x plus 8 on the right, and I can subtract the 8. So what should x equal? It should be u cubed minus 8. And now that looks like a much easier limit to deal with. Would you guys agree?
Yes.
Yeah, and it should have the same value as our original limit because we've substituted everything. Everything we substituted out, we were careful to make sure that we approached the right number and we got rid of all the x's in the right way. So now all we got to do is plug in our 2. What do we get if you plug in 2?
0, 0.
Perfect. 0 over 0, which means that we still have some more work to do. But at least now that it's u cubed minus 8, we should be able to factor u cubed minus 8. And how does that factor?
The difference of cubes.
Difference of cubes, which is on that paper I put up earlier this year. U minus 2, U squared plus 2U plus 4 over U minus 2. And now I can cancel out the U minus 2's, and those are what the problem is, right? Because if I plug in 2, that's what's giving me the 0 over 0. And we're left with 3 times 2 squared plus 2 times 2 plus 4, or 36. Any questions or issues with that?
Nope.
Everybody feel okay there?
So the difference of cubes, you put that up on a worksheet on Google Classroom, you said?
I'm pretty sure I did. I think I put up some like special cases of factoring stuff that you should know.
Okay.
Yeah, take a look for it. If you don't see it up there, let me know and I can make sure that I get it up there, but I thought I did.
Yeah, it's there. It's called the special factoring cases
Oh,
review.
perfect. Nice. All right. All right, let's take a look at another one. What do you guys think we should do with that one to start with?
Substitution. Or plug in 0 first.
Yeah, plug in 0 first. That's right. Even I was trying to get ahead of us here. So yeah, plug in 0 first. Plug in 0. What do you get?
Probably 0 over 0.
Probably 0 over 0. I don't like probably. Definitely 0 over 0, right? I mean, we should check, but if I plug in 0, I got 27 to the 2/3 power, which is 9, and then we got minus. What is this? I'll plug in 0. That's minus 18 plus 9, and then over 0. So yep, 0 over 0. And now we'll do our substitution. So what substitution should we make?
The cube root stuff.
Yeah, all that cube root stuff. So should we do cube root of x plus 27 squared, or should we just do cube root of x plus 27?
Just x plus 27.
Just the
Yeah,
x plus
just
27.
x plus 27.
Yeah, not the squared part, right? Because we don't have a squared in the second part of that. So we'll let u equal cube root x plus 27, which is going to turn this into a limit, and then the numerator will become u squared minus 6u plus 9. And we need to figure out what x is, and we need to figure out what u is approaching as x approaches 0. So first off, as x approaches 0, u should be approaching what value? 3. Good.
3, yeah.
And what does x equal? It should be u cubed minus that 27, right? So now you see why it was important to know those difference of cubes formulas, right? They're going to pop up quite often. So this denominator here is x squared, so that's u cubed minus 27 squared, and our x approaches 0 becomes u approaches 3. Good or no?
Yep.
Good.
Perfect. All right. So now we just plug in our 3, and what do we get?
0 over 0.
0 over 0, but that's okay. We're going to factor. This u squared minus 6u plus 9 becomes what? U minus 3 squared. And what is u cubed minus 27 factor to? U minus 3 and u squared plus 3u plus 9. And that x was being squared, so both of these are being squared. What cancels?
The
u minus 3 squared.
All right. So we just end up with the limit as u approaches 3 of 1 over u squared plus 3u plus 9 squared. Plug in your 3. And what do you get? 1 over 9 plus 9 plus 9, so 27 squared. What's 27 squared? Should be 729, yeah. Any issues with that? Any questions on that?
Nope.
Everybody good? All right, let's take a look at another problem.
Not only the feel of themselves, but also the.
What's the first thing we should do?
Plug in
Plug
one.
in one.
Plug in 1. What's 1 to the 1/8 power?
1.
1, so this becomes 0 over 0, which means we're going to have to find a substitution to make. Any thoughts on that?
X to the 1/8 equals U.
All right, u equals x to the 1/8. So if u is equal to x to the 1/8, we're going to need to figure out what x is. So what is x?
U to the 8th.
U to the 8th, good. And as x approaches 1, what is u going to approach?
1.
Should also be approaching 1, so we can just rewrite this as the limit as u approaches 1 of u minus 1 over u to the 8th minus 1, which when we plug in 1 gives us, again, 0 over 0. Yeah?
Yep.
Cool. So then what are we going to do with that?
We have to factor the U to the 8th minus 1.
Yep, exactly. So u to the 8th minus 1 is a difference of squares, right? It's u to the 4th plus 1 times u to the 4th minus 1, which nothing cancels yet, so what are we going to have to do? Factor it further?
Yeah.
The u to the 4th plus 1 will stay as is, but u to the 4th minus 1 should become u squared plus 1 and u squared minus 1, which once again, though, still nothing is going to cancel out, so we'll finish factoring. Limit as u approaches 1 of u minus 1, u to the 4th plus 1, it's not a 1, u squared plus 1, u plus 1, and u minus 1. Now we have stuff that cancels, right? We can cancel out the u minus 1s. So we got the limit as u approaches 1 of 1 over u to the 4th plus 1, u squared plus 1, and u plus 1, which gives us what? 1 over 8?
8.
Yep. Everybody good with that? Any issues with that?
Nope.
All right. Excellent. Everybody's good so far on all of our different limit types that we've dealt with.
I have a question about U. When you're like choosing what to substitute for it, is it just kind of like, do you have like a specific way to choose, or is it just kind of like what's making the equation like messy or harder?
Usually it's just going to be what's making this thing messy, what do I not know how to deal with, and substitute that out, and it should generally work out pretty well.
Okay.
Yep. So I had a question sent to me in the chat also. So I know that u approaches 1 because as x approaches 1, I plug in 1, and 1 to the 1/8 power is also 1. So if x is approaching 1, then u is also approaching 1 just by using this equation. Everybody good with that?
Yep.
All right. Let's move forward then. That's the last of the just like straight limit problems we're going to do for now. we're going to move into talking about the idea of continuity. Now, I know you know what a function that's continuous looks like, right? How would you describe a function that's continuous? How would you describe a function that's continuous? Somebody will say something, I'm sure.
There's no breaks or any discontinuities. It's just a solid line that doesn't like jump anywhere.
Right, it doesn't jump anywhere, it doesn't have any breaks in it, doesn't have any holes in it. No gaps, right? It's just one continuous, not necessarily line, but we'll call it a curve. So a curve that you basically could draw without picking up your pencil, right? That's what it means for a function to be continuous. Basically, that's what it means. We're going to get a little more technical and talk about what does it mean for a function to be continuous at a specific point. So for a function to be continuous at a specific point, we have three criteria that have to be met. And those are, one, the function has to be defined at that point at C. So for the function to be continuous at C, the first thing is it has to be defined at C. Second thing is the limit has to, or the limit as x approaches C of your function has to exist. So the function has to exist and the limit has to exist. And lastly, those two things have to equal each other. So function has to exist, limit has to exist, and they have to be equal at the point that we're interested in the continuity of the function. So if I have something like, here's my xy axis, something like this, and I'm talking about this point right here, well, does the point exist?
Yes.
Yep. I got a filled in circle there, right? And is the limit as x approaches that point? Does it exist?
Yes.
Sure looks like it. And
Looks like
it looks like they are equal to each other also?
Yep.
True. And therefore,
yeah.
This function must be continuous at this point. So there are three different types of discontinuities. Anybody know the types of discontinuities?
Is a whole one?
There's a hole. It's got a technical name. The technical name for the whole discontinuity is a removable discontinuity.
Asymptote.
Okay, an asymptote
Vertical.
is another one, which we call, vertical asymptote. And we call those infinite discontinuities because the function's approaching infinity or negative infinity. So we got removable. Yeah, we got removable, we got infinite, and then the last one is jump, where the function just jumps from one point to another. So these are those three different types, and I've got two different removable ones on here. A discontinuity is still removable even if there is a point attached somewhere else. If there's a hole in the function, it's still a removable discontinuity. So if we think about each of our three criteria in this first removable discontinuity, does it meet the first criteria? Is the function defined at C?
No.
No. So immediately we know this function is not continuous at C. With this second one, this other removable discontinuity, is the function defined at C?
Yes.
Yeah. So it meets the first criteria. Second criteria is, does the limit as x approaches C exist?
Yes.
Yeah.
Looks like it.
Looks like it. Yep. Second criteria is met. And third criteria is that those two things have to be equal to each other. And is the value of the function the same as the limit?
No.
No. So it doesn't meet the third criteria. So this one is not continuous at C. What about this one? The jump discontinuity.
Limit doesn't exist.
Right. The function is defined, but the limit doesn't exist because from the left-hand side and the right-hand side, it's two different values. So it meets the first criteria of the function existing, but it does not meet the second criteria. And our infinite discontinuity, the function doesn't exist at C, so therefore it doesn't meet that first criteria, and we can move forward and say that one's got a discontinuity at C also. Everybody good there?
Yep.
Yeah.
All right. So we're going to use this idea of continuity to talk about this theorem, which is called the intermediate value theorem. And you might have talked about the intermediate value theorem last year. Does that sound familiar to anybody or no?
Yeah, it's
No.
a little lost.
What? No, I heard one no, and then somebody said something else, but I couldn't quite make that out. Yes. Yes. All right. Yeah, hopefully you've heard of it, but if not, that's not a big deal. The intermediate value theorem says that if you have a function that is continuous on an interval, a closed interval, from A to B, then we can pick any number, and we'll call that number W, any number W that exists between f of A and f of B, and that for every single possible W I could choose between these two Y values of f of A and f of B, I should be able to get a C value on my function that's between A and B that when I plug it in gives me W. It sounds a little convoluted, but basically all it's saying is if the function's continuous, pick any Y value between a starting point and ending point, and we can get that Y value by picking an X value between the starting point and the ending point. Right? There's no way to not have that be the case if the function is continuous. I have to touch every single Y value from f of A to f of B as I go from A to B. I might hit some of them more than once, right? If the function did something like this, right, I might hit them more than once. But I have to hit each Y value from f of A to f of B at least once as I go from A to B. Does that make sense?
Yes.
Yep.
And so the biggest and most important consequence of this is when I have a function that, let's say, at -1 is negative and at 4 is positive, if f of -1 is negative, so we'll say f of -1 is less than 0, and f of 4 is greater than 0, that means that at some point between -1 and 4, if the function is continuous, I must have crossed through the x-axis. I must have had an x-intercept, or I must have had a 0 in there. That's the, usually if you're in pre-cal or integrated 3, they might talk about the intermediate value theorem. That's like all they say about it is that. Any questions on that?
So it's just saying like if W is between f of A and f of B, C has to be between A and B.
You can find, yeah, there is a C value between A and B that gives you W. It doesn't say that that I might be, I might be able to get W with some other value that's not between A and B. Like if my function continues like this, right, I will hit W again at a value that's not between A and B, but I'm guaranteed to hit that W value at least once as I go from A to B for any W value that's between those two Y values. Does that make sense?
Yep.
All right, let's see if we can verify the intermediate value theorem for a function on an interval. 1 second, I gotta help my son with something real quick. Okay, so our goal here is to verify the intermediate value theorem on the interval from 0 to 2 for f of x equals -x cubed. What do you guys think the first step of verifying the intermediate value theorem is?
Find f of 0 and f of 2.
All right, close. That's the second step. We have one condition that has to be met for the intermediate value theorem, and it's in the first 4 little words here of the intermediate value theorem. If f is continuous. So what do you think we should probably do before we even figure out f of 0 and f of 2?
Make sure it's continuous.
Make sure that this function is a continuous function. And this function is a polynomial. True?
Yes.
So you will want to know that all polynomial functions are continuous for all real numbers no matter what. Okay? Polynomial functions are always continuous for all real numbers.
What about rational functions before we move any further forward with this problem? Are rational functions always continuous?
Have an,
No.
No.
like an infinite discontinuity.
Right, they could have an infinite discontinuity. They could also have a removable. They could have a hole, right? So what makes that happen with a rational function? What gives you a hole or a vertical asymptote?
Denominator. Having something
Right.
in the denominator that can equal 0.
Right, putting in an x value into the denominator that makes it equal 0. But that's the only way. So a rational function is continuous for all real numbers except the ones that make the denominator equal 0. And so you can kind of tuck those facts away that a polynomial function is always continuous and a rational function is always continuous unless the denominator is 0. And you can use those as known facts as you're proving things like the intermediate value theorem. So we'll say that f is continuous on the interval from 0 to 2 because f is a polynomial. And that's a good enough explanation for why f is continuous on that interval. Everybody okay with that?
Yes.
Okay.
Yep.
So now, I'm not sure who said it before, but next step is figure out what f of 0 is. What's f of 0?
0.
0. That's an easy one. And what's f of 2?
-8.
Right. So we want to show that if we pick any w that is less than 0 but greater than -8, we will get out a c value that is between 0 and 2. So for every w between -8 and 0, there exists c on the interval from 0 to 2 such that f of c is equal to w. That's what we want to show is true. That's what the intermediate value theorem states. If we can show that if I plug in any w between here, I get a c between here, then we've done it. So how am I going to show that?
Plug in 1.
One is a value in between 0 and 2, right? But it's not the only value in between 0 and 2. So if I just plug in 1, that's showing one specific case, but it's not showing every value between -8 and 0. So if I wanted to just plug in values, I'd have to plug in literally every single value between -8 and 0, which how many of those are there?
Infinity.
Infinitely many.
Yeah, there's an infinite number of them. So that would take me a heck of a long time to test, -7.9 and -7.99 and -7.92 and -7.83 and so on to show that there's an x value between 0 and 2 for each of those. That'd take a really long time. So what we're going to do instead is we're going to say, what does w equal?
-x cubed.
Almost. It's negative c cubed, right? Because we've said that f of c is equal to w, right? So we got to make sure we plug in that c. But we could replace this w with negative c cubed because we know that we're claiming that f of c equals w. And then we can just undo this inequality. And as long as this inequality undoes to give us c is between 0 and 2, then we should be good. So we'll divide by the -1 to give us 8 is greater than c cubed is greater than 0, and then we'll cube root to get 2 is greater than c is greater than 0. And that shows us that for every w between -8 and 0, c has to be between 0 and 2 for this particular function, f of x equals -x cubed. Does that make sense?
So for any question that says to verify the intermediate value theorem between an interval, we have to do it like this, where we like show out a proof like this.
Yep. Okay. Exactly.
Oh, would it not be greater than or equal to? Or is it just greater than? Like, or
Yeah, it's just the greater than or less than. because we are choosing a W that's between -8 and 0, not including -8 and 0. So this stays as open intervals. Yeah, whenever we verify the intermediate value theorem, we always do it on open intervals, just so that we don't have an official ending point to this interval. Any other questions? All right, let's see if we can show that this polynomial has a 0 between 1 and 2. So why don't you guys take a minute or two and see if you can use the intermediate value theorem to show that. You don't need to write out the whole proof for this one because this one's not asking you to verify like the first one was, but to use the idea of the intermediate value theorem to show that it must have a 0 between 1 and 2. So take a minute and see if you can figure that out and come up with a good solid reasoning behind why that's the case. So what did you guys do first here?
Plug in 1 and 2 to the function.
All right, hopefully you did that second. First thing you hopefully did was said that f was continuous, because it's a polynomial, and then plugged those in. So anytime you're using the intermediate value theorem to prove something, state why the function is continuous. But then you plugged them in, and f of 1 was what? Negative, what is that?
-4.
-4. And what was f of 2? 32.
17.
17 sounds good to me. And then we would say that for every value between -4 and 17, right, so for any w on -4 to 17, there exists a c on the interval 1 to 2, such that f of c is w. And we know that 0, this interval contains 0. And so we know that somewhere on the interval from 1 to 2, when we plug in some number, we should get 0 for our function. And that's telling us this has a root on that interval. So by the IVT, there must be a 0 on the interval 1 to 2. Good or no? No need to like go through and unwind that whole equation to verify the full intermediate value theorem for all values. We're only interested in this singular value of 0. And we could figure out what that value was if we wanted to, although it's not going to come out to be a nice rational number, I don't believe.
So are you saying like between -4 and 17, 0 just exists between that range? So that
Yep. Yep, that
is
is
that what we're saying?
That's exactly what we're saying. So we're saying that
Okay.
the intermediate value theorem says that for any w we choose on this interval, we must be able to get a c value between 1 and 2. And since 0 is on that interval, that means that there's a c value on 1 to 2 that gives us 0, and the intermediate value theorem tells us that that's the case.
Okay, thank you.
Yep.
But if it asked us to verify, would we have to do work?
Yeah, if it asked you to verify it, you'd have to go through and write out the inequality and unwind it. I wouldn't have you do it for one like this because that's, you know, pretty much impossible to solve that fifth degree function within an inequality. So wouldn't give you one that difficult. Any other questions on that? All right. This is the last one we're going to do today, and then you guys are going to get out of here actually quite a bit early today, I think, and use your time wisely on that packet that I've given you online. So we've got a piecewise defined function, and we want to find all values of a so that f of x is continuous for all real numbers. So to show that this is continuous for all real numbers, what do you think the first thing that we should do is? Any ideas? If we want it to be continuous for all real numbers, first let's look at the different pieces of our function. We have this rational function for x values that are not -1, which what does that tell us? It tells us that this function is continuous at all of the values that make x cubed plus 3x squared plus 3x plus 1 over x plus 1 continuous, right? Well, what are those values? Should be everything except what?
-1.
-1, right? This is continuous from negative infinity to -1 and from -1 to infinity. True?
Yes.
Reasoning is because it's a rational function. Okay, so then the only thing that's left to do is to determine, is this function continuous at -1, or to find the a value that makes it continuous at -1. So we have to make sure all three of our conditions of continuity are met. So the first one is that f of -1 has to exist. So what does f of -1 equal?
A times -1 plus 5.
A times -1 plus 5, or negative a plus 5. Everybody good with that?
Yeah.
Yep.
Okay. So the next thing we need to do is we need to find the limit as x approaches -1. So how do we find the limit as x approaches -1 of f of x? Which piece of this do we look at? The top or the bottom piece?
Top.
Top piece.
Top.
Good. So plug in -1. What do you get? You get 0 over 0, right? So what do we have to do?
Factor.
Factor out the numerator. How does that numerator factor?
Looks like a Pascal's triangle.
Looks like Pascal's triangle. It's 1, 3, 3, 1. That's the third row. So that should be x plus 1 cubed over x plus 1, which is the same as the limit as x approaches -1 of just x plus 1 squared, which is what?
4.
0.
Should be 0, right? If we plug in -1 to that, -1 plus 1 is 0, and 0 squared is 0. So we've met the first two conditions. One, that the function exists, it equals -a plus 5. And two, that the limit exists, it's 0. So the third condition is that those two things must be
Equal.
equal to each other. So we just set them equal to each other to figure out the a value that makes that true. And what a value is that? A equals
5.
5. And now it's continuous for all real numbers because
It was continuous for everything but -1 because of the rational function, and it was continuous at -1 if A is 5 because it met those 3 conditions of continuity. They like to put little questions like this on the AP test, usually in the multiple choice, to make sure you can follow that definition of continuity. Any questions on that or anything else that we did today? Everybody feeling okay about limits and continuity?
Yeah.
All right. So I'm gonna let you guys go in a second. When I let you go, you should be working on the packet as much as you can. If you have questions, send me messages about it. Tonight, I'm gonna go in on the My AP Classroom, whatever it is, and assign a couple of videos for you guys to watch. Did you all get enrolled in the My AP Classroom for this class?
Yes.
Yep.
Okay, if anybody did not, if you have an issue with that, when I let everybody go, stay, and I will try to assist you in getting enrolled in the class on My AP. Sound good? Okay, and last thing is, we will have our first assessment later this week, and it's just going to be a couple of problems. You'll have just a couple of minutes to complete them. You're welcome to have your notes out for it. It will not be tomorrow. It will either be Wednesday, Thursday, or Friday. I haven't decided yet which day, and I probably won't tell you in advance, but it shouldn't be anything tricky. It should just be a couple quick things to make sure you have a basic understanding of what we're doing, and that'll be that. Any questions on that or anything else?
How are we going to take that assessment? Like,
I'll post up a thing in Google Classroom while we're in class, like a Google form or something like that, and you'll just answer it in there.
And it'll just be multiple choice, or will it be like free response?
It'll be free response.
So do we have to show our work then? Do we have to like upload anything that shows work?
Yeah, you'll just take a picture of what you write down and then type in your answer and submit. It'll give you, it should, I'm still playing around with the options on it, but it should allow you to upload an image of your work and then, yeah, but it's not going to be anything to stress over. If you've been following along and doing okay with the packets, then you should be good.